Electric potential, or voltage, is like pressure but for charged particles. I have here an electric field, or E field, which shows changes in voltage over a space. Red is high potential, blue is low potential. These arrows will show this as a vector field. Positive charges are pressured to move from high voltage to low voltage. So, this proton, with its positive charge, will be pressured to move from red to blue with the E field. Negative charges are pressured to move from low voltage to high voltage. So, this electron, with its negative charge, will be pressured to move from blue to red, opposite the E field. Now, to chemistry. Here's a basic redox reaction that we'll use a lot here. Zinc turns to a zinc ion, and a copper ion turns to copper. There are two parts, the oxidation and reduction, which combine to form the full redox reaction. These each have their own electrical potential attached to them. Electrical potential in chemistry is just how the overall pressure on charges changes after a reaction goes through. The number itself is standardized using its reduction reaction, so each reaction's potential is called the standard reduction potential. Notice that zinc here is being oxidized, so to find its reduction potential, you just flip the equation and the sign on E. But when you match the half reactions to their proper state, then you sum up the potentials of both of these, and you get the total potential of the entire reaction. So let's see how this gets used in a chemistry experiment. What I am building is a galvanic cell using zinc and copper. It starts with two beakers. The left beaker will have a 1 molar solution of zinc sulfate, and the right beaker a 1 molar solution of copper sulfate. A zinc plate is put into the left beaker, and a copper plate into the right. A wire connects the two metal plates. Then, a salt bridge connects the two metal solutions. All of these little components complete a circuit that charged particles, in this case an electron, can follow. For this specific zinc and copper cell, the cell's potential, or E0 cell, is positive 1.1 volts. You can calculate the E0 cell by comparing the reduction reactions of the two metals involved. When this reduction reaction happens, this is its change in voltage. When this reduction reaction happens, this is its change in voltage. Electrons like moving from lower to higher voltages, so the reduction reaction that creates the more positive voltage change will be preferred. In this case, that's the copper reduction. But now, the zinc reaction is no longer a reduction reaction, so it's now the reverse, an oxidation. So the sign for the voltage change flips. And adding these two numbers gives you the total potential difference over the entire galvanic cell, 1.1 volts. Okay, now I have a confession. Earlier, when I showed you that one electron moving around the whole thing like this, that was a lie. That's not what actually moves. It's close, but not that. So let's show what's actually going on by drawing all the relevant particles. Zinc metal, copper metal, zinc ions, sulfate ions, copper ions, and more sulfate ions. Buckle up, because here we go. Zinc metal is oxidized to form two electrons and a zinc ion. The ion falls into solution, the electrons move towards the wire, and the zinc plate itself shrinks slightly. The electrons, due to them wanting to move from high potential to lower potential, will flow towards the copper metal. If I measured the voltage at that point in the wire there, it would read 1.1 volts, and that would be where you, as the chemist, would extract energy for work. The electrons move down into the copper solution and react with one of the copper ions to form copper metal, growing the copper plate slightly. But now we have a physics problem. The extra zinc ion in the left solution is positive, meaning the entire zinc solution has a slight positive charge. Meanwhile, the copper ion that attached to the plate caused there to be one extra sulfate ion, meaning the entire copper solution has a slight negative charge. So, to balance the charges out, a sulfate ion from the copper solution moves through the salt bridge into the zinc solution, evening out both of the charges. And from this point on, the reaction is free to continue again. Now, another confession. All of these numbers have been at perfect standard state. Both 1 molar solutions, 1 atmosphere of pressure, and 25 degrees Celsius. How do you calculate E cell when it isn't at a perfect standard state? Answer, the Nernst equation, which comes from these chemistry identities. Alright, so let's talk about the Nernst equation, because it's paramountly important to connecting electrochemistry to thermochemistry and completing that diamond of things that compare, where we go from equilibrium to thermo to electrochemistry. So, the Nernst equation is derived from this main identity equation and this main identity equation. Basically, you take this change in G, you sub it in for that change in G, and then you take the resultant identity of this one, which is just G naught E naught right there. Because that's just saying what G naught is at standard state versus what G naught is at any one given point in time. You just sub the naught one in for here, divide by negative NF, and then you get this equation up here. That right now looks like a lot of nonsense. All of these variables, we have no idea what they really even mean. We're just plugging things in and identifying what things that are given to us in a word problem. Let's not do that. Let's instead conceptualize everything so we know what everything means, meaning that when we're given it on a word problem, we know exactly what we're looking at and what we're looking for and how these things come to be. And imagining we didn't have this, we want to know how to derive it. Let's label everything first. We have change in G, which is going to be joules per mole. I'm going to keep it in joules. I'm not going to do kilojoules. Just because chemistry prefers to have change in G in kilojoules, but it'll make it easier for me to go through the process of doing this in terms of joules. So then we have N. N would then be moles of electrons. And how you would figure out moles of electrons is, let's say we talk about our original equation that we talked about so much in the animation. Zn plus Cu2 plus forms Zn2 plus Cu. So basically what we're saying here is that 2 electrons are being transferred from side to side, because hidden inside this equation there is 2 electrons turning to 2 electrons, and because there's 2 turning to 2, they get eliminated, because that's what a net ionic equation does. But hidden inside this equation is 2 electrons to 2 electrons. If we wanted to find out what it actually was, we could just write the oxidation and reduction reactions for that, and then find out what that common number is for electrons. So what that means is that for our specific case here with the zinc and copper, we have 2 moles of electrons per reaction. This will be per mole of reaction. Oh, I wrote that on the wrong thing. That's supposed to be here. 2 mole E minus per mole reaction. Okay. Let's get this straight. This is moles of the reaction here. Okay? So now what we need to do is we need to also label what E cell is. So E cell, a lot of you would already know, is in terms of volts. And volts are joules per coulomb. That's what the actual base unit is for a volt. Of course, joule can go further than that, because joule is force per unit time, and then you can go even further from force. But we're going to stick to joules because we're looking for a thing with joules. So now what we have here is we have moles of electron and coulombs, because let's say I wanted to write this whole thing out where I do this equation, but in terms of the base units, we're looking for joules per mole reaction is equal to, we're looking for negative, and that negative I'm going to come in later as to why. We have then moles of electron per mole reaction. And then we have, with E cell, I'm going to skip over what F is for just a minute. joules per coulomb. So that means we've already filled out joule. We have that done because it's right there and there. We have mole of reaction. That's done. That's there and there. But now we have moles of electron and coulombs. Now, luckily, those are directly related. In physics, if you take physics, you know that one electron has a charge of 1.6 times 10 to the 19th coulombs. So if that's 1.6 times 10 to the 19th coulombs, then we can compare any number of electrons to any number of coulombs. Well, some random dude said way back that if you have a lot of electrons, some random number of electrons, actual electrons themselves, is equal to 1 mole of electrons. I don't exactly know what this number is, but I know that what spits out then, if you want to then compare that to how many coulombs you have, is per 1 mole of electrons you have 9.648 coulombs per mole of electron. So what F does here, this is Faraday's constant, basically tells you that for every 1 mole of electrons you have 96,485 coulombs, which is actually a stupidly large amount. Like, actually a stupidly large amount of charge. So then what we'll do is we'll do 96485. Actually, no, we're writing this in units. What is happening right now? We're writing this in units, so we'll do coulomb per mole electron. And then that completes our cycle, because then we have mole of electron accounted for. We have then coulomb accounted for. So now everything checks out there. So that's how the whole equation aspect of it works. So let's write up here, F is equal to 96485 coulombs per mole of electron. Okay, there we go. So that's our comparison there. So that means that and then that negative sign just comes from the fact that if you have a positive E cell, it's going to want to progress forward. So that negative turns change in G negative, which if you have a negative change in G, that means it wants to progress forward. So it's just keeping continuity. So that's how this whole thing works. And that's where the Nernst equation comes from. Now, let's go back to the animation and talk about how balancing them works and how this Q comes into play. Notice the one thing that isn't a constant in the Nernst equation, natural log of Q. Just a reminder, Q is basically the current ratio between gaseous and aqueous products over reactants. So let's look back at the overall equation in order to calculate Q. If there is an equal number of products and reactants, 1 molar, natural log of Q is 0, meaning E cell is equal to the standard E cell. If there are more products than reactants, natural log of Q is positive, meaning E cell decreases. If there are more reactants than products, natural log of Q is negative, meaning E cell increases. Now, for the most real-world applicable part of this unit, electrolysis. Say we wanted to make some zinc, but we only had this galvanic cell to work with. Normally, this cell will only make copper by using up zinc. The redox reaction can run in reverse though. We just need to apply an opposing voltage to it by hooking it up to an external power source, aka a battery. This is the symbol for a powerful battery, by the way. Now, the flow of electrons from the battery will be enough to make zinc by using up copper from the other side. Yes, the reaction still naturally wants to go the other direction too, but the potential difference from the battery is strong enough to overpower the normal reaction, so long as the battery itself is rated above 1.1 volts. Then, it will create a positive voltage in the opposite direction, creating the zinc. Now, let's see how a school and the AP board would test you on electrolysis reactions. Normally, electrolysis reactions look like this, where it says an electrolysis reaction forms zinc solid from a zinc and copper cell. A constant current of 2 amps is applied for 10 minutes. What is the minimum voltage that the external power supply must have in order to form any zinc solid at all? And how much zinc solid is created? So minimum voltage that the external power supply must have, well, first of all, it needs to overcome the initial voltage, which is what we were talking about earlier with the animation. So the initial voltage on a zinc and copper we know is 1.1 volts because we've seen that number so many times now. So we know that the external power supply must supply 1.1 volts, anything greater than 1.1 volts in the opposite direction in order for that to work. How much zinc is created? So we have to define what 2 amps is, because that would probably be a new thing for you if you haven't taken physics. Well, an amp is a measure of current. Current is coulombs per second. So it's basically any amount of electrons per second. Coulombs, again, can be converted to number of electrons via the Faraday constant. So let's start out with the fact that we have 10 minutes. So we know that we have 10 minutes, which is 600 seconds. And then let's just do some stoichiometry. 600 seconds, we know that this thing is C per second. So this thing is 2 coulombs per second. So we're going to see 2C per 1 second. That is our next column. Then we're going to see coulombs. We have to convert to moles now. So we're going to see 9.6485 coulombs per 1 mole electron. Then we're going to see for every 2 moles of electron, we're going to have 1 mole of zinc solid, because we're forming zinc solid, and that's just from the reaction. We know that for every 2 moles of electron, we get 1 mole of zinc solid. And then we'll just say, let's just say that this thing is asking in grams, because most of them do. I just forgot to write it. So we'll say 1 mole of zinc is, check periodic table, 1 mole of zinc is 65.38 grams. So now let's do that calculation. So 600 times 2, let's bring this closer to the camera. 600 times 2 divided by 96485 divided by 2 times 65.38 gives us 0.41. Let's just call that 0.41. Is equal to 0.41 grams of zinc formed. One of the other things they may also ask you is how much copper would be destroyed, or how much copper would go into solution after that. And then all you'd have to do is then switch this number for the amount in copper. So copper, we can have 63.55. So if we just plug this back in, but use 63.55, we get 0.395 to 0.4 grams of copper in solution. Other things what they'll do is they'll say this much solid was formed after this amount of time. What is the amperage on it? What is the current? They'll also say this much solid is formed with this constant current. How much time? They'll just switch around the order on you, but this is the basic thing of what they'll do about electrolysis. And that's how you solve a problem. One more lasting thought. This entire lesson works with liquids and gases just as much as it works with solids. A real-world case of this is actually that there's a certain voltage you can run through water to split the water into hydrogen and oxygen gas. Splitting water like this is actually the best and cheapest way to produce hydrogen gas right now, so this is the mass-produced method companies use to do that. And yes, some people suggest that when hydrogen cars become the major car type, that splitting water will be the best new way to get fuel than just extracting it from the ground. And finally, what if there's more than one reaction that can occur in the same solution or area at once? Well, let's see. As I charge up this solution, it goes and goes until the 0.34 volt threshold is hit, where the copper ion reacts and the zinc metal is left untouched. If I were to not have had the copper ion in solution though, and I charged up the solution again, once it hit the potential threshold of the zinc would turn to an ion as well. But it didn't last time because the copper impeded the voltage from ever reaching the 0.76 mark. So just also know that these reactions are preferential to whichever will occur first, if multiple can occur at once.